Good morning. There's Gabriella. All
Good
right.
morning.
Good morning. Oh, and there's a double right off the bat. And there's a Jocelyn right off
Good
the bat.
morning.
Good morning. And there's a double
Mm,
from, was that Muhammad? Oh my God, the self. Holy. Good morning. And good morning, Sydney. The voice I just heard, I think was Muhammad, but no, I'm not sure. Good morning, Sydney.
Yeah, it was me.
It was okay. That picture, I think there's something questionable about that picture, but okay. I guess at least it proves that I exist, which is also questionable. So wait. Good morning, Gabriella. Good morning, Jocelyn. Good morning, Sydney. Good morning, Rebecca. Good morning, Melanie. Good morning, Mohammed, Norma, Effie. We're still going. Wait, I know it's been a long. I feel like it's been a very long time because it has, hasn't it? No way. Wait, what's the no way? Hold on. Okay, I'm into the chat now. I might have. Oh, and good morning, Angel. And good morning. Did I say Melanie? Norma, Effie. Okay, that's the visual, the chat. Good morning, Melanie. Good morning, Angelina. Good morning, Effie. By the way, I'm a sucker for that too. We can't discuss that right now, but yeah. My 11-year-old son has finally entered the world of South Park. That is questionable parenting on my. Okay, good morning, Jocelyn. Good morning, Alexis. Good morning, Zebo. Good morning, Sydney for the triple or the double. Good morning, Nadine for the double. Good morning, Chanel. Good morning, Josh. Good morning, Christopher. Good morning, Teresa. Good morning, oh, enthusiastic Norma. Good morning, Genesis. And Alexis. Okay. Okay, Alexis and Mom, and I assume it. Wait, I don't know. I'm trying to figure out if the no way. Well, all right, I'll leave that alone. Yes. Oh my God. Oh, okay. So I guess that is about the Muhammad Sal. Okay. Good morning, Lunar. Good. Alexis. All right. There's got to be a portal just for Alexis this morning. I'm not sure what the portal would be called, but okay. I feel like she's already conducted an entire class okay. Well, I guess Muhammad. Okay, I'm gonna shut up. 1 second. This is what happens. I get just like the less I have to say, the more time I take to say it, the less energy I have, the more energized I sound. So hold on. Oh, more people coming in. Hold on. All right, bear with me for a minute. Ooh, pardon me for a minute. We're here. We're going, and we're starting a totally new topic. I mean, the good news is, well, all right, bear with me for a second. I'm sorry. Oh, oh, okay. Um, bear with, ooh, uh, okay, give me 1 second. Um, Okay. All right. I'm looking back. Okay. Oh, give me one more second. I'm looking at the exams right now, now that it is class time. So give me a second. Uh, um, I mean, um, okay, give me one more second. So what I'm doing, just so that we're clear, like, congratulations to all of you for being here right now. The fact that you are all here right now means something, is a good thing. Like, because as I think we discussed, like technically, and I don't mean to be so, I'm going to be serious for a second. Like well, all right. What I'm dealing with right now is your exam submissions, because that's like part of this deal. Um, so give me one more second if you don't mind. Um, Thank you. Okay. Okay. Um, okay. All right, I see some things in the direct chat. I see at least one question in the direct chat about the exam itself, which is an interesting question, like about the actual physics in a part of the exam, which is interesting. Good morning, Sinead. Good to see you. I I love the question. I'm not going to answer it just now because I'm not prepared because not all the exams are fully in yet, which I'll address in a sec. So I'm gonna hold on that question for now, but I'm gonna try not. In fact, I'm gonna copy and paste it so I can answer it later if you don't mind. It's a good question. I'm not prepared to actually answer that right now. Hold on. So I'm copying and pasting it into a note file. Hold on a second. Um, okay. Okay. Things are happening in the chat. I'm sorry. Okay. Okay. Um, I'm sort of waiting for a couple other things to happen in the chat, but okay, so let me back up and just say, and I don't mean to be, I want to be serious, I don't want to be somber. So this was your first exam of hopefully four with me, I mean in your life, like because you're gonna have a final exam, and then you'll have a midterm in physics 204, hopefully with me, and then a final exam. And they're all like this. Okay. So it takes a little getting used to, for good or for bad. So first of all, so the way they work always is, they have to be handed in, as most of you know, I'm just repeating, the exam gets done at home and then gets handed in time for the class period, and then you show up to the class period as though that period were the exam period, if you know what I mean. In other words, the fact that you're here right now is a good thing. I want to congratulate you for that. Every single one of you who is sitting here right now, it's as though you just showed up. Technically, it's as though you just showed up for an exam, except most of you have done the work already and turned it in. So you're here now, and that's really helpful and important. Like that's an accomplishment. In most of your cases, the fact that you're sitting here right now means you're sitting here having just accomplished something hard and that you're done with, that I hope you're proud of, et cetera, et cetera, and that hopefully you're relieved that it's over. But so even showing up, for some of you, it was an extra sacrifice. Like you might be so tired or sick of physics or sick of me that you're like, I've done the thing. Why do I, like, let me now go take a break. But you didn't. You showed up, which is great, which is your responsibility. I mean, I did tell you to do that. And, more than on a just normal day, I'm very much aware of who's here and who's not today. I mean, consciously. So if you are here at all and you can hear my voice right now, you should congratulate yourself. You did the right thing, and it is the necessary thing. And to be really blunt, the people who are not here right now, I'm aware of who, like that's part of what I was just checking a second ago. I'm aware of who they are, and you should be aware that I'm aware. You didn't waste your efforts by being here today, right now. It's part of the exam experience to show up. I will also want to say, and for those of you, and some of you, maybe you just turned in something that you're not so proud of or you're nervous about. And facing me is like the last thing you want to be doing right now. I mean, granted, it's on Zoom and all of that, but I want you to give yourself points, I mean, karmic points for the fact that you might now be walking through fear, so to speak, like, and confronting something that's uncomfortable and awkward that I might even be making more awkward. So you should recognize that I think it's a strong and powerful and not easy thing to do in a physics class. So thank you. If you are here having just turned in your exam, good job. Also recognize that, oh, well, let me go further. If for some reason you didn't turn in your exam, and there's a couple of cases, let me be clear about that to all of you. First of all, I am aware of who's turned in an exam and who's not. Like if you did the thing that you were supposed to and you got it on time, just know that I know that, and it was not wasted effort. If there are extenuating circumstances, and I said this before the exam, and I'm going to say it before the final, all that. There are things that happen in people's lives. We are human beings. Physics is not our only priority, et cetera. I know that. Um, so it is possible with these exams to give me individual notice a couple days before and say, I'm having this go on with organic chemistry or with my grandmother or whatever. I'm having this go on. Is there any way I can get some flexibility on the situation? And I'm telling you all right now, for the final exam or for the midterm of next semester, like if you have extenuating circumstances, the farther in advance that you communicate them to me, the more flexible and human and understanding I can be about them. And I will be. Okay. We have like the group's expectation, and then there's individual things that happen. So if it's not you this time, if you didn't have an extenuating circumstance or ask for compassion, but someone else got compassion or something, understand it might be your turn next time to need the compassion or the whatever. Okay. So it is possible. So that's why I say not every exam is in right now, because an individual or two or whatever had a circumstance, just so you know. Um, Now, It is also true that you do want to communicate that if you don't communicate in advance and you don't turn in the exam and like on time, so that you all know for the final exam and for next semester, do I take late exams? Yes. Because again, we're human. Like it's not all black and white situations. If something comes in late, even without communication, will I take it? Yes. Will I read it and give credit? Like, will I automatically fail the person? No. But the but the less communication there is around it, if it just comes in late and there's like no acknowledgement of that communication, there's definitely consequences, just to be clear, like points get taken off, okay? And the less the communication, the more the points. It's really about the communication, not about the circumstances. I'm saying this to you all now, not to criticize anybody. I'm saying it, well, I'm saying two reasons to be clear for the future, okay, okay, that's A. B, I'm saying it so that the couple of you or whatever who are sitting here right now with unresolved business, who still owe me something or something like that, I want to say on the one hand, you are also to be praised for being here right now, because that's really hard in a way, right? If something is a little wonky, uh, on your side, but you show up and face the music anyway to class, um, that is a very good and positive and important thing. Really, it's easy to not do that. This would be the one day that would be really tempting to not show up if you have unresolved business with me. And the fact that you know who you are or whatever, that you are showing up also sends a signal to your colleagues that is very positive and helpful and collaborative. And that's what I want to back up and say again to all of you who are here right now. Like, you are sending a signal to one another. All of you who are here right now are sending a signal to one another that you don't think you, that each one of you doesn't think that he or she or they is like above the law. I can't emphasize that enough. Like, like all of this, everything I'm saying right now, I sound really serious because it's an exam day, right? And I want it to be clear to all of you that the first thing I do on exam day is I look through and see what came in, what didn't come in, what's going on, who's here, who's not. Like it is serious. And I want you to know that so that you don't think that your efforts are wasted when you try to do the right thing. It does matter. And there's different versions of doing the right thing. Each one of you did do a right, might not have done all the right things, but each one of you has done a right thing. Possibly in the case of even facing the music and showing up here, even when your situation is not perfect, because the flip side of all this, and I don't, and now I'm going to tacitly sound critical to people who might be watching this, recording later, but I want you guys to know that if you're noticing one of your colleagues not be here right now, if you're sitting there and wondering, like, what's going on with that person? I killed myself to get this thing in and to get myself in. And are they still working on their exam right now? And is Yavram like not even noticing that? And could I have gotten away with that? Could I just still be working on my exam right now and it wouldn't even make a difference? The answer is no. Like, I want it to be clear. Like, I do know. Like, and actually, I'm going to go a step further and tell you, I will tell you for a fact, I will tell all of you for a fact, anybody who you're not seeing right now, like that is a mistake on their part. And I kind of want them to know that on the recording, or I'll talk to them. That is a mistake, but it's a mistake because it gives the impression they might still be working on the exam. And so that you know they're not. All of the exams of all the people that are not here right now are in, just so you know. Um, okay, so I emphasize all of this. I'm going to move on in a second, but I emphasize all this to say this is our first exam in physics. It's going to take me a little while to grade. It's going to take me longer than it should to grade. And I apologize for that in advance. But of course I will grade it and I'll get it back to you. I want you to know, and maybe some of you didn't do, you will find out how you did. But it's the first of, in effect, four exams you're going to take. I can tell you for a fact, especially if you either turned in your exam or you're here right now, I can tell you there's no way that you just there's no way you did bad enough to prevent yourself from passing or doing okay in this class. Like no one does. You might feel like you did, And you might feel that way when you get the exam back. Often the first exam, when it comes back, the grades are often worse than people were expecting, especially for an open world exam. Often they are, but it doesn't seal anybody's fate. No one ends up like failing the whole class because they failed a midterm or something like that. It doesn't work like that. There will be a chance for redemption and improvement after this if you need it. But you right now, what I want to say is you should be proud of yourselves. It doesn't sound like I'm saying that, but I am. I am saying I think it's a big deal to take the first exam in physics. I think it's a big deal. I think it's particularly a big deal when it seems like it should be like a no-brainer because it's open world and all of that. And I think many of us find that even with all the open resources and all of the ways in which it seems like we're allowed to cheat, it seems like it should be like not a big deal, maybe to some of us. And then it turns out for many of us to actually be a surprising, weird, big deal. You should know that I know. And you should be proud of yourself for getting through it. You should. And for being here right now hearing this, you should. Um and you should take a beat to be proud before you even worry about the grade or the outcome. You did something. It's real. I chose to be a physics major undergrad, and I chose to go back to graduate school twice after that, as many of you know, right? And then I chose to think about physics for more than 30 years, right? And I'm telling you that I find physics exams stressful to this day, even when you're the ones taking them, not me. I never didn't find a physics exam stressful. Don't think that just because I like made my life out of physics that I can't like they sucked. And by the way, also, I'm talking about in the early 90s when I was an undergrad, like from 88 to 92, and it obviously was pre-COVID and pre-AI and basically pre-internet, like not we certainly did, I mean, it was pre-online classes for sure, right? And I'm telling you, even back then, we had take-home open world exams. I had exams back then where they would distribute it on a Thursday and it was due back on a Tuesday or whatever. And we were allowed to spend the entire weekend in the library consulting all of our own notes from the class and all the books in the library. And so, I mean, it sounds old fashioned now that I say it. But I'm telling you, I didn't make up this idea of open world and I didn't make it up just because it's an online class. We could sit around all day consulting. We couldn't consult one another so much, but we could consult all the sources and the notes and blah 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 and walk around the library and work on the exam all weekend. And let me tell you, it sucked. I mean, really, it made me feel so stupid especially because I was like, I should be able to just find this in a book somewhere. Like, how is it that I can't even, right? I mean, I just so you know, I don't think it's easy if you're honest about it at all. It's so I'm here to congratulate you for being on the other side of something that's a little bit soul wrenching, I think, or can be. Okay, that's number one, and number two, to bring it full circle, one of the reasons that I let you use all these resources and all of that is because, and I think I said this at the beginning, is because the real thing about cheating to me, what's really constitutes cheating is to think that one individual has a special privilege that the other surrounding individuals don't. That's what I think is really, so as long as you all have all the same access and the same privileges and can all work together, to my mind, then we're all as a group trying to help all the individuals actually shine and show their true individual understanding of the material, blah, blah, blah. And so that's why, like, and I really believe that part of what we're trying to learn here, and particularly in lab and in lab groups where we all share the same grade and we all know how stressful that is. Don't think I don't know that that's one of the most hated parts of the physics program is that you all have to get the same grade on your lab reports when like one person did all the work and one person didn't. I know all, but part of all of that, and I hated that too. Part of all of that is that we actually are a community, I believe. And therefore, when we all show up the day that a test was due, we all show up and signal each other that, all right, I didn't get any sleep last night. Also, I'm here too, or whatever. And I don't think I'm special. Like, I think, I mean, I don't think I have special privileges. Like, that makes me really proud to be part of the community, like for real. And really hopeful about continuing to work with all of you throughout the rest of the semester and hopefully next semester. And by the way, hopefully in person, because that often is the way 204 is. I hope to see you. So, okay, that That is my speech. So congratulations on getting through your first exam. Okay. It'll, and hopefully it just gets better from here. But it'll be a little while before you find out the exact numbers. Don't worry about the numbers for a while first. Just get some sleep. Okay, so that's that. I'm gonna go on to material, but I'm looking in the chat. Sorry. Uh, okay. Got it. Got it. Okay. I hope, okay, so I'm gonna totally switch. And if you have any, well, can I? Yeah. Okay, I'm gonna move on. So I'm going to totally change the topic now. Oh, and remind me quickly in lab, are you up to, have you started lab? What's the, wait, you have Professor Lou, so you did all the board meetings about the, have you started lab 5 with Professor Lou yet?
Is that the ramp one?
Correct.
No, we only did the beta meeting.
Perfect. Good. That's actually the right answer. I mean, that was the answer I was hoping for. Great. But thank you for knowing that it's the ramp one. You're definitely on top. Okay. Um, and you can put, sorry about that little speech. I hope that little speech, I mean, well, actually, I'm gonna, as long as I just gave you that whole speech, sorry, and I will move on. But I mean, was the exam a little bit? I mean, it wasn't a joke, right? Like, I assume that it was. She's like, no, all right, that's good enough. Gabriella's face just answered the question. Fine. Okay, all right. So, yeah. Okay. And then I'm going to say another thing, too. The reason I know I get all, I won't do this every single time, but I do take these things. I think you can all tell I take this seriously. I take your seriousness of the course. And I think you guys are a very invested group. By the like for real, it's very evident to me. And as some of you know from some of the pictures, so at least one of the pictures in the yeah, so I was around late Monday night with the rest of the physics faculty, which was a rare opportunity. We were all like sitting around sort of but Professor Lou could not make it. She has 2 children, but everybody else was there. Other people that you'll have for lab next semester and stuff like that. So we were all talking about you in general terms and praising you. We think you're a wonderful group, all of, not just you. And I forgot what I was just going to say about what was my. Oh, and many of you were there late that night working on the exam. Like I know that for a fact. I mean, we and even some of you I didn't see. I heard that you. So I know you're taking this seriously, and thank you. And I know you're trying to help one another, and that's the point. Thank you. Well, okay. I'm getting myself distracted. But the other thing that I did not realize until I was taking take home exams and stuff in physics in the late 80s and early 90s um is that maybe what might have surprised some of you, and let me just say to refer to say I see you if this was like I always thought that the point of an exam in school I had thought that the point of an exam was to find out what you actually had properly learned or not up until that point of the exam. Like I thought it was like a assessment tool. I thought an exam was like let's find out if the student has done their work until this point or understands what's going on to this point. But it turns out, at least in physics exams, at least in my background experience, actually a physics exam is an experience in which you learn the material. If any of you at any moment during this exam, even for one moment, was like, oh, I get it now. Or and which is often followed, even for one moment, if you had that in the middle of the exam, you're like, oh, that's what he's been trying to say for a month, or that's what I was supposed to be thinking for a month, or whatever. If you had anything like, oh, I get it now, then by the way, for most physics students throughout the ages, certainly including me, that feeling is usually followed up by something like, oh crap, I'm such an idiot. Or oh crap, it's so simple. What the hell? Or oh crap, he's such an ass. Why didn't he just say this a month ago? Right? It's usually followed instead of just being like, yes, I get it now, which is what we should feel. Usually the feeling of getting it in physics is followed by, well, what motherfucker, like what WTF? Are you serious? It's just that? It's just that I've been banging my head against for a month. Why couldn't he just say that? Or why didn't I just do that? Right. That always happens. If that's ever happened to you, that happens to everybody. And if it's in the middle of an exam, depending on your sense of morality or scholarship, often it's also then followed by like, oh, it's kind of weird that I'm figuring this out right now. I guess I was supposed to know this a week ago. It's kind of weird that I'm figuring this out in the middle of the exam. Am I kind of cheating? I mean, I just got this from freaking Khan Academy or something like that. Like, or my friend. Like, let me tell you, no, 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 no. That's actually the point of the exam. The point of the exam is to raise the stakes and create the conditions so that you're so your brain is finally forced to snap into realities that it wasn't snapping into before for whatever reason, right? The point of a physics exam is to learn the thing in the middle of the exam. If you had any of those moments last night, you're doing the right thing. You're not cheating and you're not stupid. And don't be angry at me. I mean, you can be, but like that's actually how it works. Okay. And there's a very funny thing in physics how every single time we figure something out in physics, what we're figuring out is something that actually makes sense. So we always then think, oh, it made sense the whole time. Where the heck was I? It's so dumb. It's obvious. It is obvious, but it's not dumb. And neither are you. That is how physics works. We are trying to figure out truths that once we figure them out seem so truthful, we can't see how it could be any other way. And we can barely remember how it was or why it was that we didn't get it 5 minutes ago. That's how it works. So every time we figure something out in physics, what we should do, and I'm still working on this, over 30 years later, what we should do every time we figure something out in physics is go, oh, yes, that is awesome. I am smart. Like, I just figured that out. Oh, that's great. Instead of being like, oh, I'm so stupid. Why didn't I know that before? Like that is the goal of all this is to transform that way of thinking. If I didn't believe that, I could not be talking about these same ideas every single day, 3 times a day for 30 years. It's always interesting to me because that process is always interesting and that process is different in every single person. The physics doesn't change, but all of you do every single semester. So like just so I'm going to shut up now, but if you had any moment like that at all, in the last 3 days where you're like, oh, then yay, then purpose served, tuition, money amortized. Like, really? Okay, so now we move on to Newton. Newton was born the year that Galileo died. Galileo died in 1642, in the beginning of 1642. Newton was born in, some say Christmas of 1642, and some people say a couple days later, like around New Year's of actually 1643, but right at the end there, it's unclear. Right at the end, the thoughts of Galileo passed into the body of Newton, maybe, and then Newton started doing his work in England until he died in 1727. As I'm sure you're aware, but we're now going to expand. Well, Newton's big work was called I mean, Newton had a lot of works, but his signature work is this enormous, thick volume called the Principia Mathematica, Principles of Mathematics. Um, and he outlines a lot in this book, a lot. But among other things, as you know, he establishes the 3 laws of motion, which become fundamental to physics. Hold on. So I call them like N1, N2, and N3, as in Newton's first law, Newton's second law. Now you know these laws, or many of you have heard these laws. But I want to give you our perspective on these laws and how they function in this class, or yeah, in this trajectory. So, and there's different, people use different words to capture these laws. Of course, they were not written in English in the first, well, not of course. He did write them in England, but he wrote them in Latin. So any words we use to capture this are not exact, but some words are better than others. Here's how I would write the first law. You know what? I'm not changing this, but I'm running out of, I'm going to write this bigger on the next page. This is, you can keep, I'm going to keep saying the same thing. I'm just going to make it bigger. Sorry. Okay. I'm going to read it out loud. Okay. I know you've heard this before. I mean, I believe most of you heard this before. First of all, my handwriting, it says, so this is Newton's first law of motion, right? Unless acted on by a net external force, an object at rest stays at rest, an object in motion stays in motion at the same speed in the same direction. Okay. In a way, much of it sounds totally obvious, perhaps, especially if you're used to it. And in some ways, some of it is not totally obvious. I'm going to make some comments about it. Okay. The thing about good, good. Yes, direct chat person. External forces are like friction and air resistance. Okay. There's a question in direct chat where someone says, "Are external forces like friction and air resistance?" So my fast answer is yes. Good point. Good observation. And I'm now I'll expand even a little bit further and say what external forces really or net external forces really ultimately they certainly can include friction and air resistance. But in broadest terms, what net external force means to me is any other object in the world influencing the object in question. So totally great question, and this is what am here to say. Like if you look at this law, it says unless acted on by a net external, and yeah, and there's a lot of words in here that we haven't seen before yet that we're going to expand on. But it says unless acted on by a net external force, an object at rest stays at rest, an object in motion stays in motion at the same speed in the same direction. So the structure of this law, like if you look at my subpoint B here, my comment B, the structure of the law is that we're given a condition. We're like, assume this condition, no net external forces acting. And now we're going to divide it to two possibilities under that condition. Like either we're going to be assuming that no external forces are acting on an object, then the object either we're talking about an object that happens to be at rest or we're talking about an object that doesn't happen to be at rest. Those are the two options, right? So first of all, this condition, which the direct chat person's asking about, the condition has this fancy language, net external force. But honestly, what I'm here to tell you all is that what that condition really means is uh, when it says unless acted on by blah, 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 it really means unless influenced by any other object in the world. Like whether that other object is air molecules or a table or a rug on the ground or some other object bashing into it. What we're looking at in the first law, the reason it's the first law is we're looking at like the base case. We're going to develop, Newton is going to develop three laws of motion that are to help predict, how objects move through space and time. And so what he's doing is sort of starting with the base case, the simplest, most natural state of objects, like what would we expect how would we expect an object to move when it's not being messed with by any other object? It's like the simplest like case possible in a way, the purest case with no other variables or distractions. And it's kind of like the control of the thought experiment. Like before I get it, okay? So to say no net, so technically net means sum of, SUM. Like net means add up a bunch of things. Add up all the external forces. External means from the outside. Force means influence. So a net external influence, a net external force really means some kind of influence from outside the system. And the system is an object. So outside the object means some other object. Okay, so first and foremost, and you'll see why I'm making a big point of this. Hopefully you'll see in a moment why I'm making a big point that Newton's first law is asking us to investigate what would a single solitary object be expected to do on its own under the most natural or uninterfered with of cases. So then Newton comes along and says, well, sorry, I'm looking at there's things in the chat. Sorry. Right, right. Same direct chat person. Yes, she or he is following up. Right, I'm with you. Good. Um, right. I think I see. Okay, I'm going to get to this in a minute. But so the person there's a couple people in direct chat, uh, again, demonstrating what an invested class you are. So the person is saying like that they were wondering what he ever observed that did remain at the same speed. How could he have ever observed anything that wasn't impacted by other stuff like air resistance or friction? Wouldn't there always be deceleration? It's a very good question. So maybe I'm not making the question clear to everybody else. Let me address that in a moment when I expand on these two possibilities. Okay. And on that too, someone else in the direct chat is saying, would gravity, wouldn't gravity count as a net external force? Isn't gravity a net external force on something? And then the person's saying, gravity is not an object, but it like does make a force on things. Okay. And in a way, we're getting ahead of ourselves, but in a way not. Gravity totally does count as a net external force on things. Yes, gravity is the force of interaction between a thing and planet Earth, or at least in the context that we talk about it right now. Like gravity is the name of the force, but it's an influence from another object called Earth in most cases. So indeed, Newton's first law is trying to describe something where not only are we not taking into account air, as one person in direct chat is asking, but also, right, we're not even taking into account gravity. We're not talking about gravity in the first law. That is true. So what we're talking about in the first law is in the extreme case might be like a meteor or a rock of like a rock in deep outer space. That would be one extreme, which granted Newton never went to deep outer space. I know, but one kind of example of an object that really doesn't have any net external forces acting on it appreciably would be that like a meteor in outer space, deep outer space, like far away from Earth or far away from the moon or which such things do exist and they are possible to conceive and they're even possible to study. But of course, you're right to suggest we're not in deep outer space and neither was Newton. But let me go a step further. For what Newton is picturing in the first law, because this is a worthwhile challenge, sort of from two people in direct chat. What Newton's a more realistic version, a more accessible version of what Newton's picturing in the first law would be like a puck on ice, or in old term, like a box on like a pond of ice, which Newton certainly could have observed, right? Or in slightly more modern terms, maybe a puck like on really good ice, like Zamboni ice, like in an ice hockey rink, which would be smoother ice than they had in the 17th century, but not so much smoother that in the 17th century you couldn't. Anyway, you could picture a puck on an ice skating rink would be a very good sort of system or situation to consider if you're trying to think of what Newton's first law is. Or if you want to go a little bit higher tech than that, picture a puck on an air hockey table, which are, I mean, I don't know how many of you have ever played air hockey, but like in an arcade or whatever, but like it's fun and it's fun for a reason because it's a Newton's first law machine. I mean, what the puck does uh, is what this is saying here. So let me get what is being said here. Oh, wait, oh, you're the oh my God, Alexis is like, there's totally going to be an Alexis portal. And I mean, it's awesome. It helps the class. It makes me feel like we're, yeah, okay. Okay, just okay. I'm gonna make a so I can stay on this and also address your comments. Okay, I'm gonna back up for a second. These are great quick because I think I know what's behind these concerns in the chat. I think so. Let me say the prediction Newton's first law is saying when nothing is messing with a solitary object, here's what we'd expect the solitary object to do. If the solid, so case one, or I mean, option one, if the solitary object happens to be just sitting there when we walk in the room to observe it, if it's a hockey puck that's just like sitting on ice and we walk in, we see the hockey puck sitting on ice, then what we would expect is it's going to continue to sit on ice, right? I mean, and I don't think anybody, right? That's possibility one, is if there's an object that is not under the influence of friction or gravity or somebody pulling it or a piece of string or anything like that. If there's an object that seems to be isolated from external influences, if it happens to be sitting around at the moment we start observing it, then what we would expect is it will continue to sit around. That's claim one. Now, I'm pretty confident that the two questions in the chat and that most of any of your thoughts are not worried about case one. Like, I think most people probably are like, yeah, duh. right? And in fact, most people then were like, yeah, in fact, Newton's not at all the first person to say that at all. Like Aristotle was saying that 2,000 years before. That's not actually, I mean, it may be very important. It is very important, but it's not really the surprise or the controversial part of this. It's the second possibility that's leading to these questions in the chat, I think. The second possibility, Newton says, now, if there's a puck on ice and you walk, and when you walk in, the puck happens to already be in motion, like someone already hit it with a hockey stick, or whatever, and it's already like moving toward one bank, one wall of the hockey rink, or whatever. If when you walk in and start observing or taking measurements on this hockey puck, if it happens to already be moving, Newton's saying it's going to keep moving, and it's going to keep moving in a straight line. Like it's not going to change its direction, and it's not going to spontaneously change its speed. Like Newton is saying, it's not going to speed up. And you're like, yeah, or slow down. Now, and that is the law. That's the law. It's like things that are sitting still are going to keep sitting still. Things that are moving are going to keep moving. And of course, most people, and this is the part that is new. This is what Aristotle totally did not say. And it's not expected that someone would say this necessarily. Of course, what most of us intuitively think, if we're thinking about how does the world naturally work, what is the natural expectation of an object, we tend to think that the natural expectation of an object is to slow down. If you leave it alone, if you don't help it, we think of objects as needing help to keep going. Many of us think that. And that if we don't help an object, eventually it's going to slow down and stop. So this claim, when Newton says, no, an object naturally is just going to keep going, it's not going to slow down. And then we go, wait, really? What? I mean, are you serious? Like, didn't you not know there's like a gas crisis? Like, there's like, why do you think we always have an energy crisis? And like, we pay all this money on gas and everything to keep cars going. Like, what are you talking about, Newton? And then, as at least two people in the chat, figured, like, then Newton says, no, no, wait, I'm not talking, hold on. I'm talking about like the natural, like kind of extreme, kind of idealized case, it seems, of like not friction, not gravity. If you get rid of the friction and you're talking about a puck on ice, not a rubber tire on the pavement, you're talking about a puck on ice. Newton says, that's what I'm talking about. Did you read my condition at the top of the law? It says, unless acted on by a net external force. But now, many of you, I'm not trying to have an argument with you or something, but I'm assuming that at least two of you in the chat are being polite and respectful, but are kind of like, really? I mean, really? That seems kind of technical, yo. Like, you're giving me the natural state of objects, what they would do if they were left alone, but you're like, and you're trying to be like a scientist, and you're saying, here's like the science of motion, and you're saying to us, but what I'm talking about is like a puck that has like no friction on it. So like, either like a really, really, really good hockey rink that hasn't even been invented yet, or like something in like deep outer space that you haven't been. Like what it seems like, I feel like it's possible that at least two people in the chat are saying, isn't this a little bit like fantasy world? Like, where did he come up with? Why, how, and why is he talking about objects that have no friction on them or no air resistance on them? Like, first of all, how did he ever experience that? And second of all, why do I care? Because like that's not the world. I mean, I'm not saying that anybody said that in the direct chat, but it certainly would be fair if they did. It may be kind of what's on their mind. It certainly was on my mind when I first, but here's the deal. How he came to make this claim and why it's important. Yeah, it's an idealization, but it's not a fantasy. It's an optimization, but it's not a lie. What it is calculus, the concept of calculus, not all of the, like one of the reasons you need calculus for this class. Now we're going to use calculus in a really big explicit way in the next class, like second order partial differential equations. Like, believe me, if you want to, like the mechanics of calculus will be big in 204. But right now, what we're dealing with is the actual concept of calculus, which is not an easy concept. What I mean is this statement, Newton's first law, it's really a statement about limits and asymptotes. How he knows what it would be like for there to be no friction on an object, even if he's never been to outer space, or even if he doesn't have a Zamboni yet for his ice skating rink, right? How he knows is the same. It comes from Galileo first, is what Galileo did was he put an object on a surface that was pretty rough and he flicked the object. I mean, he did it in a very controlled way, controlled circumstances, but imagine taking a puck on a rug and flicking it and watching as it slows down. And it would. A realistic puck on a realistic rug will slow down and eventually stop, right? After like, let's say a meter. But then you smooth down the rug a bit. You remove some of the friction. You make it a little bit smoother and you flick this and you control the circumstances and you flick the puck again. And this time, as you of course know, the puck is going to go farther before it stops, right? It's going to take more time before it starts appreciably losing speed, right? And then if you smooth down the rug more and more and more, and then you make a graph out of your findings, you will find that the smoother and smoother and smoother you make the surface, like the more and more and more you approach a zero friction scenario, the more and more farther and farther the puck is going to go, the more and more time it's going to take before it starts losing its speed. And so what you do is a process called successive approximations, not successful, successive, like one after the other after the other. This is what Galileo, so part of what Galileo brought to us as part of the scientific method was this idea of, of looking at the pattern, getting closer and closer and closer to perfection so that we can extrapolate from the curve of all the data from the graph so that we can extrapolate what would be happening as we approach perfection and noticing that the closer and closer we get to no friction, the closer and closer we get to a situation of no velocity change, right? So we can extrapolate that in the limit, if there were really no friction, we'd really have no velocity change. And the reason that's relevant to do that is the same reason in calculus that we do this is that then from there, we now know the shape of the realistic function in general that actually lives with us in our real lives. Do you see what, like, in other words, this is not this is an extrapolation from increasingly close data that then tells us it then tells us what to predict when the Zamboni gets better and better and better in the future. What and it allows us now to say, oh, and it basically is saying we can study the effects of friction so closely that we know how to isolate and separate the effects of friction from the actual natural state of the object unto itself. Like what we're trying to do here is separate variables. Basically, what I'm saying in the end is this is a statement of asymptote that you, if that helps at all. And it only starts to become possible to think this way. It's not a coincidence because the man who's helping us think this way, and other people and women are the people that are developing a formal mathematical way of saying that in our finite brain, we can develop a rigorous mechanism for approaching and extrapolating and predicting what happens in the infinite cases. Right. So the answer is that, like, how did he get to this conclusion? Successive approximations, taking things to the limit, seeing where the asymptote was, even if we never could get to the asymptote, we can get closer and closer. And why did he do this? So we can separate variables. So from here on in, we can make predictions about what objects do by themselves, and then add to that what will objects do when they influence each other. So I don't know if that. So what this law is saying is, on the one hand, if something were just sitting around, if something were sitting around by itself, it would continue to sit around. If something were moving by itself, it would continue to move by itself at the same speed and at the same direction. And if it doesn't, it's because there's some other kind of influence on it, like friction. And the extent to which it will do this is the extent to which the other influence is minimized. There's a lot. So comment D is, if you stand back and think of this law as two possibilities, one which is like self-evident and obvious, but the other one of which seems controversial or new or kind of a stretch, which I think most people do think of this way. And again, it's true. Historically, the first case everybody already understood and agreed since, 200 BC. The second case is where Newton really seems to be saying something new. If that, and possibly weird, if that's the way you view the law, then here's really the logic of it. If you really think about what this law is really saying, I think, and I think this is the part that might be new to some of you, like it sounds like the law is saying there's two different cases, the case of zero motion and the case of motion, right? And it's saying that in either case, velocity should not naturally change. That the velocity of a single object should remain constant, should naturally remain constant, whether that object has zero velocity or the object doesn't have zero velocity. The surprising part is when we say it should remain constant even when the object does not have zero velocity. Like that's a surprising part. Again, I'm just taking a guess here that that's why at least two people in the direct chat were sort of pressing on that because that's the part that seems weird. And it does seem weird. But if you really step back and you think about everything we've done to physics in to this point, particularly with Galileo's principle of relativity, what you realize is that what Newton's actually saying, the bothersome part of what Newton's saying is zero is not a special case. If you really think about what this law is saying, it's saying that for a single object, the natural state of a single object, whatever that the natural state of a single object is to maintain constant velocity. The natural state of a single object is to not accelerate. And Newton is saying that should be true whether the object happens to have a zero velocity or not. And most of us tend to think, well, it's probably true if the object has zero velocity, but I don't think it's true if the object doesn't have zero velocity. What Newton's saying is zero velocity is not a special case. And do you know what? Like he's saying, either way, I don't care. Whether you're sitting still or moving, you should not spontaneously accelerate. That's what he's saying. You being an object. If an object, whether an object is sitting still or moving, it should not spontaneously accelerate. And all of us are like, well, yeah, if it's not moving, it shouldn't spontaneously accelerate. But if it is moving, it should spontaneously decelerate. That's what all of us tend to think. But if you really think about it, what what this is really saying to say that zero is not a special case, what we're really saying is if you really think about it, all Newton's first law is saying is that Galileo's principle is true. And it's not a coincidence. It's not plagiarism. Like it's directly coming from Galileo. It is not a coincidence. If you really take Galileo serious, I'm saying, you know how we have five forms already of Galileo's principle of relativity? The sixth form is known as Newton's first law of motion. The sixth form of Galileo's principle of relativity is what is known as Newton's first law of motion. If you really stand back and think about the words and think about the concepts and think about the objections or the questions that are being raised in the chat, it actually all does fit together. What we're saying is single objects don't have velocities on their own, right? Velocity was always a comparison, never, it was always a relation between two objects. It was never a property of one object. So to say that an object is sitting still means compared to something, always. There is no object that is literally in and of itself sitting still. Just like motion is a comparison, right? So what we're really saying is if you really think of velocity as in the eye of the beholder, right? Like right now, I'm stationary relative to the floor. The floor is stationary relative to the earth, but the earth is not stationary relative to the sun. I am not stationary relative to the sun. Or if I'm on a subway, I'm stationary relative to the subway, but I'm not stationary relative to you if you're on the platform, right? So ask yourself, what do you expect? If you're like, I think objects that are sitting still should continue to sit still, but objects that are in motion shouldn't continue to be in motion at the same speed, right? If you think, well, think about someone on a subway. If I'm on a subway and they're like, or I'm on an airplane and I've got a tray table and there's like peanuts on my tray table, right? From my point of view, those peanuts should not spontaneously ever start accelerating. Like they should just continue to sit there. Everybody would agree with that. The peanuts should just continue to sit there. But if you're watching through the window of my airplane, you're not seeing peanuts that are sitting there. You're seeing peanuts that are continuing to move forward at constant velocity. That's not a trick. I'm saying, like, right? It's just a different perspective. You wouldn't say that the peanuts are objectively sitting still. You would say that they're sitting still compared to me. And that's why I'm not surprised that they continue to do that. But they continue to do that by continuing to move forward and not slow down or anything from someone else's perspective. Right? It would be really weird if the peanuts just spontaneously all of a sudden moved to my mouth. But that is what it would look like to me if the peanuts spontaneously started slowing down, which is what we all think of. Do you see what I'm saying? Things should spontaneously continue the same velocity that they ever had before. To one frame of reference, that will be zero. To another frame of reference, it will be non-zero. Zero is in the eye of the beholder. There's no reason the law of physics should be different for the zero case than from the non-zero case. That was Galileo's original principle. The laws of physics hold the same in all, at all constant velocities. So here's the first law of physics, and it's literally just saying that. It's saying, yeah, that is so true that our expectations for single objects should be the same, whether we think the object's going zero or not zero, because zero and not zero are just in the eye of the beholder. Do you see it? So I'm going to move on. I know we only have 5 minutes. But what I'm here to say, really, so I mean, I couldn't have planned it more. The people that brought up things in the chat, yeah, like that is the point of the discussion. That is the classic discussion. I'm saying and I know you've all heard Newton's first law before, and most of you, and you've thought about it before. I think the new information here, if there's anything I'm trying to teach right now, it's that what Newton's first law really is Galileo's principle of relativity. What all of physics really is Galileo, including Einstein, is Galileo's principle of relativity. If you just keep tweaking it and tweaking it, or applying and applying, you see, no matter how fancy and complicated physics gets, it's the same idea, just revealing itself layer by layer and layer. The idea is that speeds are not special. And speeds are not a thing all object has. Speeds are comparisons objects bear in relation to others. Okay, so that's the first law. I know we only have 4 minutes. Okay. Second law, you've all heard. And I know we're running out, so I'm just going to write them quickly in a second. I'm just looking at my color scheme here. Sorry. Yeah, okay, so the second law. Second law, also very deep and very expansive, but an expression much simpler and mathematical. You've heard before. The second law is this. Okay, very quickly. I know we have 2 minutes. Oh, yeah. Yeah. Right. So the second law is that big symbol is a sigma, like for math, sigma like sum of, and the arrows over the letters mean vector. So the second law is that the sum of all net external force vectors on a mass produces the acceleration of that mass. Or the way I wrote it here, the acceleration of a mass is directly proportional to the sum of all external forces acting on that mass. But what's key to this, so it's the sum of, right? So you could say F net, you could say net force or sum of forces, same thing. But the key is that force and acceleration are vectors. So what this is really saying, I know we have 1 minute, what this is really saying in three-dimensional space, it's really saying, like, if you remember Galileo's principle about vectors, it's really saying that the sum of all the forces in the x-axis equal the acceleration in the x-axis, while at simultaneously but independently, the sum of all the forces on the y-axis produce the acceleration of the mass on the y-axis and etc. with the z-axis. It's really three separate equations happening independently yet simultaneously. Now we have to, that's the one we're going to use the most in class mathematically. We're going to use this all over the place. Obviously, we only have 1 minute now, so I'm not going to expand further on it now. But F net equals ma is a vector equation. And it says that the sum of all the force vectors equals the acceleration vector. The last law, I'm just going to write it and then we're done for today. The last law you've heard as like the action reaction law or whatever, but I'll say it in simplest terms right now since we only have 1 minute. The third law is if I push you, you push me back, you push me with the same magnitude of force. The third law is if I push you, you push me back, but with the same magnitude of force. I mean, there's a fancier way to say it. I'll say the fancier way next week. But the third law is that forces always come in pairs. The third law is that force is a symmetric relationship between two objects. If I push the wall pushes me with the exact same magnitude of force. That's the third law. Obviously, we're going to talk more about this next week, but it is 10:40. So congratulations to all of you for being done. Take a break. You're not going to get them back this Monday. I apologize. I just want you to know that I can't, I'm not going to do them that fast. Like there's another, but I'll do them as fast as I can, but it'll take a little while. Okay. So have a great weekend. And I'm here if there's any questions. Have a good day. Yes. Have a good day. Okay.
Thank you.
Thank you. Have a good one.
Have
Yes.
a good day, Professor.
Have a good day. Thank you. Good to see you. Good picture.
Yeah.
You have a good one.